To escape the slowness of checking every single item, we need to introduce a fundamental constraint to our data: structure. Specifically, the items in our list must be sorted in a predictable order, such as ascending numerical values. When a dataset is scrambled, an item at any given position tells us absolutely nothing about the rest of the list. But once the data is perfectly ordered, a single point of information unlocks a massive advantage. Knowing the value at one specific position tells us definitively whether our target lies ahead of that position or behind it. This predictability forms the absolute prerequisite for a much faster approach, allowing us to navigate through data with deliberate intent rather than blind guessing. To navigate this sorted terrain efficiently, the binary search algorithm tracks three specific positions using variables called pointers: low, high, and mid. The low pointer starts at index 0, the very beginning of the array, while the high pointer marks the very last index. Together, they establish the boundaries of our active search window. To inspect the data, we calculate the exact middle index using a straightforward mathematical formula. We add the low and high values together and divide by 2. Because array indices must be whole numbers, we drop any fractional remainder using integer division. The resulting index is where we place our midpointer, splitting our search space directly in half. With our pointers established, we can perform the core decision logic that makes binary search incredibly fast. We compare our target value directly with the value located at the midpointer. If our target is greater than the value at mid, the sorted nature of the array guarantees that the target cannot possibly exist anywhere to the left of our middle point. In an instant, we can discard that entire lower half of the dataset. To reflect this on the next step, we smoothly adjust our search window by sliding the low pointer to the index immediately to the right of mid. By changing just one variable, half of the remaining data is eliminated from consideration. Now we can observe how these mechanics form a continuous loop to systematically isolate a target value. With our new, smaller boundaries, we recalculate the middle position. Once again, the mid-pointer drops down into the center of the updated search zone. We perform another comparison. If the target is still larger or smaller, the boundaries squeeze inward yet again, isolating a tiny fraction of the original array. This iterative halving process repeats rapidly, narrowing the active search zone down to a single element. When the value at the midpointer finally matches our target value exactly, the algorithm successfully stops, confirming the precise index location of the item. We must also account for the scenario where the item we are searching for is completely missing from the dataset. The algorithm handles this naturally through its pointer movement rules. As the search loop continues and the target is not found, the low and high boundaries keep closing in until they point to the exact same final element. If that final element still does not match our target, the pointers are forced to cross paths on the next step. The low pointer shifts to the right of high, causing the search space to mathematically collapse to 0. This crossing condition indicates that the entire array has been searched, prompting the algorithm to exit and safely return -1. The mathematical efficiency of this divide and conquer strategy is exceptionally powerful. If we map out every decision made during a binary search, the path forms a balanced binary tree where each step cuts the remaining work precisely in half. In computer science, this performance profile is measured using big O notation and is classified as logarithmic time complexity, written as O log n. To understand its real-world scale, searching through a dataset of 1 million items takes a maximum of only 20 comparisons. Remarkably, if we double that dataset to 2 million items, binary search only requires one single extra step to find the answer, proving its incredible scalability for modern, massive data systems.